Hello, everyone. Thank you for coming. I'm Luke Robitaille. I was a member of the 2016 Texas National Math Counts team. We won the contest, and now us 4 members are teaching you some classes. So it seems that today's is the last one, but we have time for it at least. So yeah, I'm a sophomore in Texas. I'm homeschooled, and so yeah, that's about me. If you have questions about the math or about whatever, please, if you want more explanation on the math I'm about to talk about, you can email Andrew Kai, another member of the team, at andrewkai31@gmail.com. So, okay, that's some preliminary. So let's get some math. So today's topic is number theory. And so, you might wonder a little bit, number theory? Well, isn't all of math number theory? After all, we're doing theory and we're dealing with numbers. Isn't it number theory? Well, when we say number theory, what we mean is sort of the properties, specifically problems concerned with the integers, not just any numbers. So it's a little bit of a misnomer, but yeah. So today, number theory specifically is concerned with properties of the integers. So that's what we're talking about today. And in particular, one important thing, you might be wondering about when a number is divisible by another number. And, what are a number's divisors? And one important thing is, when is a number prime? What special properties do prime numbers have? And so let's start with prime numbers. So most of you likely already know what a prime number is. Basically, it's a positive integer p greater than 1, where it's only positive divisors, and I'll just say divisors. Like technically, I guess -2 is a divisor of 6, but like when we say divisors, and when just about anybody says divisors, it's sort of implied that they mean positive divisors. So the divisors of 6 are 1, 2, 3, and 6. For our purposes, and for 99% of the world, you can assume you're not counting -1, -2, etc. And these are the divisors of 6, because 6 divided by 1 is an integer, 6 divided by 2 is an integer, but 4 isn't a divisor of 6 because 6 divided by 4 isn't an integer. So yeah, basically when I say divisor, I mean positive divisor. So so a prime number is when its only divisors are 1 and itself. So 7 is a prime number because its only divisors are 1 and 7. Okay, so prime numbers are really, really important because of this thing called the fundamental theorem of arithmetic. Is one of the biggest reasons why prime numbers are so important. And basically what it says, oh, and I should specifically point out, 1 is not a prime number. Because it makes our lives easier to say 1 is not prime. We can define the word prime to mean whatever we want, but for our purposes, we want to say 1 is not prime. Okay, so the fundamental theorem of arithmetic says if for any positive integer, you can write it as the product of prime numbers in exactly one way. So if I have 180, or let's do 60. If I have 60, I can write 2 times 2 times 3 times 5. These are all prime numbers. And this is the only way to write 60 as the product of prime numbers. Sure, like you could write them in a different order. Maybe I could write 3 times 2 times 2 times 5 or something. But the point is, it's the same prime numbers, just in a different order. There are the same number of 2s. There are the same number of 3s. There are the same number of 5s. It's the same everything. And so this is the same as this, basically. And so the fundamental theorem of arithmetic tells you every positive integer is like this. So 60, you have this. And we can write this quicker as just 2 squared times 3 times 5. So, 2020, or just a simpler example, let's do like 4 is just 2 times 2, or 2 squared. 77, well, that's just 7 times 11. Or, 5, well, you would just, there you go, it's 5. It's prime already. You can just have the product of one prime number. It's itself. Or here's one that might seem a bit tricky. 1, well, how do you write that as the product of prime numbers? Well, we'll fudge around with our definitions a little bit to make this as nice as possible. And we'll say that if you have the product of no prime numbers, it's 1. So like, that might seem a little bit weird. If you multiply 3 times 5, it's 15, sure. If you have just 5 as a product, okay, it's 5. And so I'm going to, take a big leap and say that the product of nothing is 1. It makes our lives easier. So yeah, there you go. The product of nothing is 1. Okay, so, and with that caveat, the fundamental theorem of arithmetic works, and it makes a lot of things about the integers really nice. And so, it shows you that the prime numbers are sort of the building blocks of the integers. And so they're really important because, if you want to know about the integers, the prime numbers will build up the integers. So yeah. So one example of how you can use this is like, if you want to understand an integer's divisors. So if I have this number 60, and I'm going to write its prime factorization in a particular way. Let's write it as 2 squared times 3 to the first power times 5 to the first power. And then, so then where I'm, 3 to the first power is just 3, etc. So then how many divisors does it have? And what is their sum? Well, there are formulas for this, and I'll briefly talk about why they're true, is that let's add 1 to each of these exponents and then multiply the results together. So 2 plus 1 is 3, 1 plus 1 is 2, 1 plus 1 is 2, 3 times 2 times 2 is 12. And so 60 has 12 divisors. Actually, okay, good. Because, if you want to make a number that's a divisor of 60, well, it can't have any primes other than 2, 3, or 5. And then, so you could write it as 2 to some power, maybe 0. Maybe it's 2 to the 0 power times 3 to some power times 5 to some power. And so, if this is to be a divisor of this, well, this is 0, 1, or 2. It can go up to 2. And this is 0 or 1. And this is 0 or 1. And so in each case, the number of choices you have is the exponent over here plus 1. So 2 plus 1 is 3, so I have 3 choices. 1 plus 1 is 2, so I have 2 choices, 2 choices. And so just make all the choices independently. And so you have 12 choices. And this would work whatever you do in place of 60. And again, 1 has 1 divisor, but that's trivial. Let's when I tell you about any integer, maybe I should say any integer greater than 1. So what I just did will work for any integer greater than 1, and then just 1 is a special case. It has 1 divisor. The sum of its divisors is 1. But 1 is kind of, you can deal with 1. You know how to deal with 1. Okay. And then what about the sum of the divisors of a number greater than 1? Well, it turns out that if you look at like all these divisors, if you think about the distributive property very carefully. The sum of all these numbers is just what you get when you add up all the possibilities for each of the things in the number. So basically, so the product of the divisors of 60 would just be 2 to the 0 plus 2 to the 1 plus 2 to the 2, multiplied by 3 to the 0 plus 3 to the 1, multiplied by 5 to the 0 plus 5 to the 1. And then you can just evaluate this. It's just 7 times 4 times 6. And if you attended our geometric series lecture last week, you can see our sequences in series lecture last week, you can see that these are geometric series. And so if you add big numbers, you might be able to evaluate the numbers, these sums easier using the formulas you learned then. And hopefully the video will be up soon. But if you didn't attend that lecture, that's fine. It's, you can still follow this lecture. And the video of that, we hope, will be up soon. So anyway, yeah. So we hope the video of that will be up soon. But anyway, in this case, it's just 7 times 4 times 6, which is 168. And you can see this, if you just, maybe what I said about think carefully about the distributive property isn't very obvious. It's not that clear, maybe. But basically, like if you expanded this whole expression out, sort of like FOIL, like, when you say first, outer, inner, last, or whatever the thing is, taking every term, but sort of bigger. In this case, you'd have 12 terms. And like, look at every way you could make a term. Well, say I took that, then that's a divisor. And like every divisor you could get in exactly one way. So the terms are just all the divisors. And so the sum of the terms is the sum of the divisors, but the sum of the terms is just the product. And so that's why this would work. So that's, so if a math contest asks you to find how many divisors a number has, some number greater than 1, how many divisors it has, or how many divisors it has, or what's the sum of its divisors for some positive integer greater than 1, just find its prime factorization and then do this technique. So, for example, just take a minute and do this for 1800. So just quickly, I'll give you like 1 minute-ish. Just apply exactly the same technique. So think about this for like 1 minute. All right, so just to quickly go over it, you could factor 1800 as 2 cubed times 3 squared times 5 squared. Just make a factor tree or whatever they taught you in school, or however you want to do it. You can get the prime factorization. Just divide out 2 and then divide out 2 again until you get to an odd number, and then divide out by 3 until you stop doing that because you get to something that's not a multiple of 3, and keep going until you hit 1. But yeah, just get the prime factorization. You probably have heard about this before. So then the number of divisors is just 3 plus 1 times 2 plus 1 times 2 plus 1, which is 36. And then the sum of the divisors is this. And then you can just see that this is 15 times 13 times 31, which is 6,045. And again, these are geometric series. And so, you know, if you haven't already, check out our check out our sequences and series class from last week, with hopefully a recording coming soon to our website, to the website. So, but yeah, you might want to check that out at some point in the future. But if you haven't seen it again, it's okay. But yeah, so you could, you know, find it pretty. The point is that you can just, you know, it follows fairly easily without me having to list out 36 numbers and add them up one by one. You know, you don't want to do that. And so let's do some problems. So, or let's do a problem. So here's a problem from the AMC 8 a while ago. What is the smallest positive? What is the smallest positive integer that is neither prime nor square, and that has no prime factor less than 50. So none of it, so it doesn't have any prime factor that's less than 50. And it's not a prime or a square. So what's this? So yeah. So take maybe like 90 seconds to 2 minutes to solve this problem. So think about it, and then I'll come back and tell you about the solution. So take a minute or two. Okay, let's talk about this problem. So basically, let's call the answer n. So let's look at n's prime factorization. And so, okay, we know none of its prime, it doesn't have any primes in it that are less than 50. So what are the smallest prime numbers that are greater than 50, that are at least 50? Well, 50 isn't prime, 51 isn't prime, 52 isn't prime, 53 is prime, but not 54 or 55 or 56 or 57 or 58. 59 is prime. And you could keep going and find more and more primes, but we'll actually only need those two. Okay, so it might include some primes greater than, so we want some primes greater than 50, but none less than it. Or greater than or equal to 50, but none less than it. So, it's not 1 because 1 is a square. And so look at its prime factorization. It can't just have one prime number. Like if you write the whole prime factorization out, it's not just one little prime number. It has to be at least 2, because otherwise it would be prime. So then, or it could be 3 or more. But if you wanted to have 3 or more, it would be at least 53 cubed, which is a very big number. So, and keep that in mind. Or you could just have 2 prime numbers. And so if it's the same prime number, then it would be a square, which is also bad. So it would have to be 2 different prime numbers, which is at least 53 times 59. And so, one way it has to be at least this, or the other way it has to be at least this. And you can see that this number is way bigger. So we want to do it this way. So, like this way will, probably give us smaller numbers. And you can see that, in fact, this number, 53 times 59, it works. It's not prime. It's not a square. It has no prime number factor less than 50. So this number, 53 times 59, since it's less than anything you'd get the other way, is the answer. So the answer is 53 times 59, and then, just, how to multiply numbers. This is 3,127. So that was a problem. So we solved it. All right. So let's get on to some more things. Let me tell you about Legendre's formula. Just quickly. So I don't want to spend too much time on this, so you should definitely, go look this up on Wikipedia after this lecture is over. But for now, I want to tell you about it at least a little bit. And so basically, if you have a positive integer n and some prime number p, and then you wonder, what's the exponent of p in the factorization of, in the prime factorization of n factorial? What is this n factorial? Well, it's just 1 times 2 times 3 times all the way up to n. So for example, 6 factorial is 1 times 2 times 3 times 4 times 5 times 6, which is 720. And just to write out this word, this is factorial. F-A-C-T-O-R-A-I-L. Sorry, I-A-L. And yeah, these numbers can get really big. Like, 100 factorial is some massive number. To use a technical term, we could say that it's really big. I'm joking about a technical term, but yeah, these can be really big numbers. So you don't just want to like directly prime factor them. So you might want to use some of the fact that it's already somewhat factored for you, and then like you can end up getting a formula. Like just in a nutshell, if you can look at the fact that it's already broken down for you somewhat into this, and then like look at how many multiples of how many times p occurs in the factorization of all of this whole thing by looking at how many times p occurs in each of the little factors. And then you can look at how many factors of p there are, and then how many of these numbers are divisible by p squared and p cubed and so on, and you get some formula. And then you can, which looks like this. So if you know what the floor function means, you know, it looks like this. You would eventually get that this is the answer, where the floor function means the greatest integer less than a number. So for example, the floor of pi is 3. And this can be computed easier ways, but like there's another shortcut, which is what, you know, you might want to remember. So you can do it this way. But another way is to think of it as S is the sum of the digits of n in base p. Like write n in base p and then take the sum of its digits. Then the answer, the exponent of p in n factorial, is n minus s divided by p minus 1. And it's not obvious, like none of this is really that obvious. It's not that clear why this should be equal to this. And it's not that clear why either of those should be equal to the exponent of p in the prime factorization of n factorial. But it's all true. Look it up. It's Legendre's formula. And just, you know, to give you a little bit of an example, you know, you could say, you know, the sum of the digits of 52 in base 5. Well, you could write it as 202, which is 4. So the exponent of 5 in 52 factorial is 52 minus 4, because 2 plus 0 plus 2 is 4, divided by 5 minus 1, which is 12. Okay, so that's Legendre's formula, and I want you all to get a chance to practice a little bit with Legendre's formula. So let's quickly do one practice problem with it. So here's a problem from a past AMC 8. So for any positive integer m, the notation m factorial denotes the product of the integers 1 through m, which I already told you, so you know. So what is the largest integer n? For which, and the notation, it's an exclamation point, for which 5 to the n, and you know, I've been, you know, the example I showed you was where p, the prime number is 5, but of course, you know, you could do this for any prime number. It's not that 5 is the most special prime number. You know, any prime number will work in Legendre's formula. So for which 5 to the n is a factor of the sum 98 factorial plus 99 factorial plus 100 factorial. Or equivalently, you could just ask, what's the power of 5 in the prime factorization of this number? So you can use Legendre's formula on this problem, but not just like right off the bat. So again, let me give you, so you'll need a little bit of algebraic, maybe some algebraic cleverness, and then Legendre's formula will be useful. So let's take 2 minutes and solve this problem. So take 2 minutes and solve the problem. All right, so maybe you solved it, maybe you didn't. So let me show you how you would go about solving this. So first of all, these are some big numbers, but you can sort of factor out, like, what do you do with a big sum? Well, you might want to factor it. And so notice this, okay, this 98 factorial, okay, 98 factorial. 99 factorial is 99 times 98 factorial. 100 is 100 times 99 times 98 factorial. So this sum, if you factor out the 98 factorial, or let me write this as 1 times 98 factorial. Well, maybe I shouldn't erase that, but whatever. It's 98 factorial times 1 plus 99 plus 99 times 100. And now this sum, 99 times 100 is 9900, plus 99 plus 1, that's just 10,000. Now you can use Legendre's formula. 98 so 98 in base 5, you would write it as 343. You can figure that out. And so the sum of the digits is 3 plus 4 plus 3 is 10. And so 98 minus 10 over 5 minus 1 is 22. So 5 appears 22 times in the prime factorization of 98 factorial. And then you can just see it appears 4 times in 10,000. And so in total, because this is 10 to the 4th power, which is 2 to the 4th power times 5 to the 4th power. So in total, 22 plus 4 is 26. So 5 appears 26 times in the prime factorization, which will give you, that's the answer. And if you didn't want to, go through this stuff about like writing it in a different base, again, there's this other way, which is just like 98 divided by 5 is 19 with some remainder. Ignore the remainder. 19 divided by 5 is 3 with some remainder. Ignore the remainder. 3 divided by 5 is 0 with some remainder, so you can stop and then just like add up the numbers. Ignore the 0 because 0 plus anything is just the thing. And 19 plus 3 is 22. So that's another way you could do Legendre's formula. But either way, that's Legendre's formula. And so I really want to talk about some important topics. So let me tell you about modular arithmetic. And so basically the idea with modular arithmetic is that basically, suppose I write out the integers starting from 0. Normally you would write them along a line that sort of just goes off to infinity in both directions. But let's write them not on a line, but on a circle. And maybe we want to wrap, so let's wrap around to where, where you write 7 at the same point as 0. And 7 is fairly arbitrary. I could have done this with 10 or with 73 or whatever. But so let's do, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, etc. And you could also go backwards, -1, -2, -3, and so on and so on. And so then let's say that and eventually you've got all the integers, and then you can sort of think of it almost as a clock face. So then let's say that all the integers that are sort of at the same point on the clock face, they're not exactly equal, but they're sort of like almost equal. And so we would say that they're congruent modulo 7. And this is sort of, the intuition behind it. So formally, we would say that for a positive integer d, and then integers x and y, then x is congruent to y modulo d, or normally we would just say mod d, if and only if x minus y is divisible by d. And so I wrote this, so this thing with the 3 bars, it looks a lot like an equal sign, which has 2 bars. And in fact, they behave very similarly. Not exactly the same. There are important differences, but they behave somewhat similarly. So in particular, okay, let's fix some positive integer d. And so I'm just going to write a lot of congruences, and let's just assume that all the congruences are mod d, modulo d. So, okay, first of all, anything is congruent to itself, modulo d. This is good. I will write modulo d here. So, it's, if one thing equals another, then they're equal in the other order. And I'll start leaving off this mod d. Normally you should write it, but like, I don't feel like writing it over and over again. So another thing is like, it's also transitive. If one thing equals a second thing, one thing is congruent to a second thing, which is congruent to a third thing, then the first thing is congruent to the third thing. So it behaves like equality should. And then also, if let's say I have 2 things now, a is congruent to b mod d and x is congruent to y mod d. Then it turns out that the sums are congruent modulo d, which is what you would expect if this were actual equality. So this is good. The differences are congruent modulo d. The products are congruent modulo d. Also, if I raise one of these congruences to any positive integer power, say n, if n is any positive integer, then a to the n is congruent to b to the n mod d. Like if you have a is congruent to b mod d. So yeah, it has a lot of properties. There is an important caveat. There's an important thing that you need to be aware of. Notice, I mentioned addition. I mentioned subtraction. I mentioned multiplication. I did not mention division. For example, you can see that 28 is congruent to 18 modulo 10. But what if I want to divide both sides by 2? I would get 14 and 9. Those are not congruent modulo 10. I drew a big slash mark through it. They're not congruent modulo 10. So yeah, be careful. Don't try to do division. There are some ways in which you can say that maybe division will work under, some circumstances or whatnot, but basically don't try to do division when you're working with moduli. Moduli is the plural of modulus, which is what we would call the number that we're taking mod. But yeah, don't try to do division if you're, basically you see it, you'll get into problems. And so, don't try to do division, or, you might end up thinking you've proved something and it's false. So yeah, so don't try to do division. And so one way of thinking about moduli is that, like, if I have some number n, and then when I divide it by d, say the remainder is r, then n is congruent to r mod d. So, when I divide 29 by 7, the remainder is 1, and 29 is congruent to 1 mod 7. Another way of thinking about it, at least, and this way you should think of it strictly for positive integers, is that if two numbers have the same last digit, when I write them in base d, if two positive integers have the same last digit, when I write them in base d, then they're congruent modulo d. So in base 10, which, is what we usually use, then, 38 is congruent to 168 modulo 10. Because in base 10, which, is what you would write them in, they have the same last digit, and they're both positive. And notice, you want to be careful about negative numbers. 18 is not congruent to -8 mod 10. And so you can treat the negative numbers in a special way, and so you can make some caveat, but for now, just don't worry about that. For any positive number or 0, if they have the same last digit, then they're congruent in that base, and vice versa. If they're congruent and they're both positive or 0, then they have the same last digit. And so I don't have much time, but later you should look up. So I'm going to skip over. So let me skip over these, but definitely there's something I'm going to skip over, but you should definitely go look it up on your own time. So look up Fermat's little theorem, or also known as, just Fermat's theorem. But its Wikipedia page is probably called Fermat's little theorem. And there's sort of a generalization of it, like something that is more powerful than Fermat's little theorem that applies in more situations, called Euler's theorem. And these are both important, and you should, look them up. But I have only 15 minutes left, so I'm going to skip them for now. Sorry, but look them up, they're important. So let's do a problem. Or here, actually, let me give you 2 problems. And let's take 2 minutes to do both of them. So these were both on the AMC8 within the past 10 years. So, okay, problem 1, or should I say part A, look at this as a problem with 2 parts. Part A, find the units digit of 13 to the power 2012. And part B, find the tens digit of 7 to the power 2011. So let's take, I guess, like some time and work on these problems. So solve these problems, or try to solve the problems. I'll be back soon. All right, so let's talk about the solution to this problem. So basically, the point is, if you have the units digit of this number 3 to the 2012, well, we might as well just look at it as, since the units digit means we can just think of mod 10. So we might as well just see 13 mod 10 is just the same as 3. So let's look at 3 to the 2012. And so since it's mod 10, we can just focus on the units digit. So 3 to the 1 is 3, times 3 is 9. 9 times 3 is 27, so let's just look at the units digit is 7. 7 times 3 is 21, so just the units digit is 1. And should I say 3 to the 0 is 1. And now look, we're back at 1. And so every 4 numbers we'll continue, we'll keep going and hit 1 every time. So so for any power, you can figure out what it is mod of 3. You can figure out what it is mod 10 by just looking at what the exponent is mod 4. And so 2012 is divisible by 4. And so this number is just where it is in this, it just hits the 1 on mod 10. So the units digit is 1. So that's that part. Now, the tens digit of 7 to the 2011, this is a bit trickier. And so the point is that there's not a modulus that's going to help you with just the tens digit, because mod 10 tells you about the units digits, but it doesn't tell you about anything else. And notice that I can look at the units digits because these are positive numbers that we're dealing with. So mod 10 tells you about the units digits, but it's not going to help you with the tens digits for numbers like this in this case. So what we're going to do is we're going to look mod 100. So what mod 100 does is it tells you about the last 2 digits of a number. So if you look at the last 2 digits of powers of 7, you start off with 7 to the 0 is 1, which we can just write as 0, 1. 7 to the 1 is 7. Okay, 7 times 7 is 49. So 7 to the 2 is 49. So 49 times 7 is 343. The last 2 digits are 43. 43 times 7 is 301. Hey, look, we're back to 1 again. And so again, it will just repeat in this cycle of 4. And it's just a coincidence that the cycles happen to be 4 both times. But you can, you'll get such cycles eventually for whatever number, modulo whatever, but the cycle might be different. It might not start from the very beginning. It might be longer than 4, but that's the point with these exponents. And so look, now it's just a cycle again. And so again, what this is will just depend on where 2011 fits in this cycle. And so 2011, when you divide it by 4, the remainder you'll get is 3. And so 2011 fits on the same place as 3. So the last 2 digits of 7 to the 2011 are 43. So the tens digit is 4. That's the answer. And for problems like this, where you have these exponents and you want to figure out how they work modulo something, these exponential things, and you want to know how they work modulo something, those theorems I told you about, Fermat's little theorem and Euler's theorem in particular, are very useful. Look them up on Wikipedia. And so look them up on Wikipedia later. And now, it's 5:54. I'll just tell you, I don't have much time for this either, but there's another important theorem called the Chinese remainder theorem. And what this basically tells you is that if you have 2 different moduli, so say I was looking mod 7, but someone else is looking mod 12, and then yet another person is looking mod 11, say. Let's say that all the moduli are like relatively prime to each other, so no two of them have any common factor greater than 1, then what it basically tells you is like they're independent of each other. They don't sort of affect how each other work at all. So in particular, if I specify what I want a number to be, modulo each of these, say I want it to be 1 mod 7 and 3 mod 12 and 10 mod 11, then some number will fit all those constraints. If all the moduli are pairwise relatively prime, if no two of them have any common factor greater than 1, and in this case, these do. 7 and 12 don't have any common factor greater than 1. Neither do 7 and 11, neither do 12 and 11. So in this case, like, that's basically what the Chinese remainder theorem says. This is also important. You should read more about that later too. And so I'm going to give you all a couple more problems. We might go a few minutes over time, but I think this is important. So, okay. So here are a couple more problems. So sort of on separate topics. So, okay, problem 1, I'll say. Okay, Lou has the number 3 to the 2017. So now he writes it all out and he takes the sum of the digits. So he makes a new number by taking the sum of the digits of this number. Then he makes a new number by taking the sum of the digits of that number. And he continues until he gets to a 1-digit number. So the question is, what's that 1-digit number? Basically, like just summing up the digits repeatedly, what's the 1-digit number that he would get at the end? And then problem 2 is basically, okay. Mrs. Sanders has 3 grandchildren who call her regularly. So the first grandchild calls her every 3 days. The second one calls her every 4 days, and the third one calls her every 5 days. So the problem is say they all called her on December 31st, 2016. On how many days in the next year did none of them call? So like how many days were there on which they all simultaneously didn't call? And so you can do this using the second problem, you can do this using you'll want to think about the Chinese remainder theorem some more. And like in particular, really that idea about the moduli being independent of each other. And I'll tell you more about it when we solve it. And so just use your intuition or whatever. And then for this problem, you'll want to think about like, what moduli makes sum of digits nice? And so try to solve these problems. Take like 4 minutes or something like that to try to solve at least one of these problems. Or here, actually take 2 minutes and then we'll solve the first one and then take another 2, and then I'll give you another 3 minutes to solve the second one. And I know it's 6 o'clock now, so if you have to go, that's fine. There will be a recording. So thank you for coming. And if you have any questions, again, you can email andrewkai31@gmail.com, but I'll go a little extra, so I hope some of you can stay to solve these last two problems. So if you have to go, that's fine. If you can stay, please stay and try to solve these problems. And if you have any questions, that's the email address. But yeah, so if you have to go, that's fine. If you can stay, let's work on problem 1 for about 2 minutes. So let's talk about this problem 1. And so the idea is basically like, the key to the solution is this fact, which is that if you take the sum of the digits of a number, then the new number is congruent to the old number modulo 9 if we're working in base 10. Because basically the idea is like, if you write some, if I have some number 784 and I write it as, 7 times 10 squared plus 8 times 10 plus 4, then like if I look mod 9, 10 is congruent to 1 mod 9. So mod 9, the number is congruent to if I change all the 10s to 1s here. And then this is just the sum of the digits. And so we're happy. So that's why that's true. And so whatever numbers Lou writes down, all the numbers are congruent modulo, each number is congruent modulo 9 to the previous one. So in particular, the last number is congruent to the first number modulo 9. But look, 3 to the 2017, that's 3 times 3 times 3, but we don't even care about all the 3s. All we care about is the first 2. It's a multiple of 9. So 3 to the 2017 is a multiple of 9, so it's congruent to 0 mod 9. And so the end is also congruent to 0 mod 9. And you can see it's some positive digit. And so it has to be 9. That's the only digit that's 0 mod 9. So it is 9. All right. So 9 is the answer. Eventually he'll end up with 9. And so let's quickly, let's take about 2 to 3 minutes on this second problem. So try to solve the second problem. So yeah, try to solve the second problem. All right, so let's solve this second problem. So, okay, so we're looking, so the stuff about the date, like you don't care that much about the date. The point is just like, it's 365 days because 2017 isn't a leap year. So basically, like if you want to write it in terms of purely math notation, the question is how many of the numbers 1, 2, 3, all the way up to 365 aren't divisible by 3, 4, or 5. And so the Chinese remainder theorem will actually tell you that about this like being independent is that like a combination of residues mod 3 and 4, since 3 and 4 have no common factors, it's just the same as a residue mod 3 times 4 is what it'll turn out to be. And so like a residue, a combination of residues modulo all 3 of these is just a residue modulo 3 times 4 times 5. So 3 times 4 times, because there are no 2 of 3, 4, and 5 have a common factor. So, and again, I might be going a bit quickly, but if you have trouble, you should look up the Chinese remainder theorem later. And in particular, this problem is 2017 AMC 8 problem 24. So let's look at this interval. So it's basically, you can look at it as 1 through 60, because remember, 3 times 4 times 5 is 60. And then you can go to 61 to 120, and then 121 to 180, and similarly to 240, and to 300, and to 360, and then just the last 5 numbers. So in each of these intervals of 60, it contains exactly 1 copy of each residue mod 60. So how many ways can you choose a residue mod 3 that's not divisible by 3, and a residue mod 4 that's not divisible by 4, and a residue mod 5 that's not divisible by 5? Like, basically, the residues mod 3 are 0, 1, and 2. Mod 4 is 0, 1, 2, and 3. Mod 5 is 0, 1, 2, 3, or 4. So basically, we have to choose 1 or 2 mod 3, 2 choices. 1, 2, or 3 mod 4, 3 choices. 1, 2, 3, or 4 mod 5, 4 choices. 2 times 3 times 4 is 24. So there are 24 combinations of these residues that aren't divisible by, that make a number not divisible by any of these 3. Meaning there are 24 residues modulo 60 that aren't divisible by 3, 4, or 5. That won't give you a number divisible by 3, 4, or 5. So there are 24 numbers like what we want in this interval, and this interval, and in each of these intervals of 60 numbers. And then at the very end, what about these? Well, mod 60, at this point you just count. 361 isn't divisible by 3, 4, or 5. 362 isn't, but 363 is divisible by 3. 364 is divisible by 4. 365 is divisible by 5. So that's 2 more. So there are 6 of these intervals with 24 numbers like what we want in each. So 6, and then 2 more. So 6 times 24 plus 2. 144 plus 2 is 146, which is the final answer. And so that's the answer. And so, yeah, and so there's lots more I could have said, but I think we're already long enough over time. So yeah, look up the Chinese remainder theorem later, and Fermat's little theorem and Euler theorem. There are lots of good things. If you have questions, you can email andrewkai31@gmail.com, as I said before. So thank you all so much for coming. Stay safe, everyone.